Okay, so welcome everyone to the second discussion session of the day. So Anna, the floor is yours, as you wish.
Thanks. Yeah, so if people have questions, let me know now, or perhaps I can briefly sort of tell you what the idea was of the first lecture. So we were looking at the asymptotic symmetries of asymptotically flat spacetimes. Okay, and what we found last time is that these are generated by vector fields psi mu, whose essential feature is that they're a function of two things. So one of them is this f of z and z bar, which is a function on the sphere. So on the celestial sphere at infinity. And the other one is a vector field on the sphere. Okay. And in particular, one can, well, we said last time that these guys, so if f is non-zero, but y is equal to 0, then these are supertranslations. While if one sets f equal to 0 and leaves y at this point arbitrary, these would be super rotations. But in fact, what one finds from an asymptotic symmetry analysis is that these y vector fields are not arbitrary. They actually have to obey the following conditions, that dz yz bar is equal to dz bar yz is equal to 0. Okay, and so let's for a moment, or in fact, I just focused on this case last time. So let's just set f equal to 0. So of course, in general, both f and y would be non-zero, but let's just restrict to a subgroup of the asymptotic symmetries of asymptotically flat spacetimes, which have f equal to 0. Okay, so these are going to be labeled by these yz and yz bars, which obey these conditions. And you may notice, so that, as I said last time, that solutions to these equations locally take the form yz proportional to z to the n. Let me just try z to the n, and similarly for yz bar. Now, perhaps I haven't made it clear last time, but these yz's actually generate the Virasoro algebra. And one way to see that is to define some new generators, Ln, which are defined to be z to the n plus 1, d by dz. And then you can compute their commutators, namely Ln, Lm, and you find that this is going to be equal to n minus m, Ln plus m. And this is nothing but the Virasoro algebra. Oh, this is a bad color. Let's see. Virasoro algebra with c equal to 0. And similarly, so this is a holomorphic copy of the Virasoro algebra. There is an anti-holomorphic copy of the Virasoro algebra generated by similar L bar ends. Okay, but of course, these are not globally well-defined on the sphere, but there are also global solutions to these equations, which are nothing but the Lorenz transformations. So globally, we have 6 vectors. So dz, zdz, and z squared dz, and similarly for the z bars. And these generate the Lorenz group. Or equivalently, their algebra is SL2C. It's the SL2C algebra. So the take-home message, and this is very important, is that the asymptotic symmetry group of asymptotically flat spacetimes includes an infinite dimensional subgroup, which is labeled by these YZs, which are essentially conformal killing vectors on the sphere locally. Yes? Okay, so this is point number 1. And then, so in other words, we are familiar with the Lorenz. Let me just summarize. We are familiar that the Lorenz group is a symmetry group of Minkowski space, for example. And we said last time that asymptotically flat spacetimes are spacetimes which revert to Minkowski at infinity. So it's not surprising to say that Lorenz symmetries are a symmetry of asymptotically flat spacetimes. What's more surprising and comes out with a careful symmetry analysis is that this Lorenz group gets enhanced to 2 copies of Virasoro. Okay, and these are called, so together with the super translations, which are these vector fields, which in addition to being labeled by YZs are also labeled by non-zero Fs, they form the extended BMS group. But this particular subgroup, which has F, these super translations set to 0, is called, well, goes under the name of super rotations. Okay, and now that we have these vector fields, one can ask, well, what's the action of these symmetries on radiated data? So in particular, one can ask what the action of these xi's, so these have, again, I'm just restricting to f equal to 0 and y non-zero, on something like CZZ. So remember that the derivative with respect to retarded time of CZZ is something that we called the news. And this can be essentially thought of as data one can specify its cry minus, which then is sort of can be thought as a boundary condition. And then once one can then evolve this data and arrive with some S matrix, for example, and then arrive at some other data at cry plus. Okay. But in any case, the symmetries act on these. Oh, and this is also the transverse traces component of the metric. So we'll see that it's related. Its quantization is related to gravitons. But one can work out what the action of the symmetry is on CZZ, and one finds a linear piece. So this is going to be. It's in the notes. It's some sort of y-dependent factor differential operator which acts on CZZ. But more importantly, there is a piece which is a linear shift, so which is independent. It's an inhomogeneous shift, which just depends on this third derivative with respect to z of yz. So this is a linear transformation, and this is a shift. And so the logic now is that one can imagine that this symmetry action is actually generated in the quantum theory. It's going to be generated by some kind of operator, which we call Q, and which acts on CZZ as a commutator But because of this sort of shift into these two pieces, one can also split this net charge into two pieces. So one of them we call the hard charge. So this would reproduce its action on CZZ would reproduce this this first term in the transformation, so this guy. And then there's going to be another term which we call the soft charge, which is supposed to reproduce this shift, this YZ dependent shift in CZZ. Now, one can write down explicit expressions for both Q and, well, for Q hard and Q soft. And it turns out that this Q hard is quadratic in NZZ and CZZ. And this can be seen. So how can we see this? We can see this by recalling that NZZ and CZZ obey the canonical commutation relations. So you can see that these are sort of like on the phase space, right? This NZZ is like a momentum and this CZZ is like a position operator. So you're going to obey some canonical commutation relations, which are going to be proportional to delta. Oh, sorry, here I should say CWW. And this would be evaluated at U, ZZ bar. This would be evaluated at some U prime, W bar. And this commutator is going to be proportional to delta functions. So delta functions in Z minus W and delta function in U minus U prime. Okay, and using this commutation relation, you see that in order to reproduce a term like this one, right, this Q hard has to be quadratic, right? So, some integral over the sphere of some terms, some sum over terms which are quadratic in NZZ, and one can work out this expression basically by matching onto this action of the symmetry on CZZ. And similarly, one can see that this other term in the net charge. Yes, Igor.
Oh, hi. I want to start by apologizing for flooding your Slack channel with questions. So here, just a very silly question. If I go to Stronger lectures, he motivates the separation between the soft and hard part from the antipodal matching condition. Now you are using the commutator relations at this crisis.
I'm going to get to that, but the split into soft and hard parts, I think, is not okay. I may be wrong, but it's not a consequence of the matching condition, right? The matching condition is going to be a matching for the full charge. Okay, we're going to see in a moment that it's the full charge that has to match across spatial non-infinity. So between scri plus minus and scri minus plus. But the split into the hard and soft piece, as we're going to see in a moment, is due to the fact that, you know, there's two contributions in the action of the symmetry on CZZ, and one of them is linear in CZZ and the other one is independent on CZZ. And similarly, the charge is going to have a term which is quadratic. So as a consequence, the net charge, the total superrotation charge is going to have two contributions. One of them is going to be quadratic in N and C, and the other one is going to be linear in N. And in particular, we call this the soft charge, as we're going to see in a moment, because its insertion, essentially its insertion into the S matrix is equivalent, or related rather, to an insertion of a soft graviton. Okay, this is why we're calling it a soft charge. It's a piece linear in the news, and in a moment, I didn't say this last time in the lecture, but it's a very easy way to see why this would generate, this would be related to a subleading, well, in this case, subleading soft graviton.
Oh, I see. Thank you very much.
Yeah, thanks for the question. Okay, so this is linear in NZZ. Okay, and once you understand this split, okay, one can ask, what constraints does this charge or the symmetry impose on the S matrix? So what are the constraints? But at this point, with what I said so far, there are really no constraints on the S matrix, because here I've worked out the action of the charge. So this the charge on data at Scri plus, and as I said last time, but there is a similar, one can define a similar analysis. So near, let me say, so far we're near Scri plus, but similar analysis can be done at Scri minus. So let me just illustrate this here. So we have an asymptotically flat spacetime. So this is Scri plus from last time. This is Scri minus. And we have some charge, which we call Q, which is defined on Scri plus. You can see from the notes. There is another charge, Q, let's call it Q minus to distinguish it from Q, which is defined on Scri minus. Or equivalently, one can also show that both of these guys are actually can be written as just boundary terms, and they can be shown to just act at Scri plus minus and Scri minus plus respectively. So I'm calling Scri plus minus is the past boundary of Scri plus, and Scri plus minus is the future boundary of Scri minus, right? And so far, just by doing from the symmetry analysis I just did, Q and Q minus are unrelated so far. And in particular, the symmetries, and in fact, this is the essence which in fact Andy has solved. The essence of the problem Andy has solved about 8 years ago is that people didn't know how to define scattering in asymptotically flat spacetimes. And the reason why they didn't know how to define it was that people knew about the BMS symmetry, but the BMS symmetry had two components, one of them acting at Scri minus and the other one acting at Scri plus. And these BMS and BMS plus and BMS minus groups were independent of one another, which essentially meant that if you specified, so say you're now trying to define scattering in asymptotically flat spacetimes. So let's say I specify my data on this Cauchy slice, which is Scri minus, then I evolve it with the S matrix, and I'm going to end up with some data at Scri plus. But this evolution with the S matrix is not going to fully determine my solution, my outgoing state on Scri plus, because we just showed that the data, whatever we get at Scri plus, is going to be determined by the data at Scri minus, but only up to a BMS transformation. Okay, so there is this freedom which is allowed by essentially having these two groups, two symmetry groups acting independently at Scri plus and Scri minus. And so here comes a very important point, which is that actually one can restrict to a diagonal subgroup of this BMS plus BMS minus symmetry by imposing a matching condition. So the matching condition essentially equates these two charges. So there are some constraints which one can impose essentially on these functions yz and on the angular momentum aspect at Scri plus minus and Scri minus plus, which result in this sort of conservation law. So to see that, one can look at the following representation of the superrotation charge. So this essentially can be written as y, z, and z bar. Sorry, this would be an integral at scri plus minus over y, z, and z bar, y, z bar, and z, where this is the angular momentum aspect I discussed yesterday. And these are just these conformal Killing vectors on the sphere. And so if one imposes that yz, okay, and so there is a similar expression at scri minus plus. And so if one imposes that both yz and nz match across spatial null infinity, so sort of that they match at scri plus minus and scri minus plus. So we have yz at scri plus minus is equal to yz at scri minus plus. But by this equality, I mean antipodally. By antipodal, I sort of wrote it yesterday, but the coordinates, the antipodal matching essentially tells you that if you have a sphere at scri minus plus and another sphere at scri plus minus, and here say you have coordinates z and z bar on one sphere, and a priori we're going to have coordinates w and w bar on the other sphere, one is supposed to match this point here by its antipodally related point on the other sphere. So in other words, there is a relationship between z and w telling you that w is essentially minus 1 divided by z bar, and similarly for z bar. So this is what I mean by antipodal matching condition. And similarly for nz at scri plus minus is equal to nz bar at scri minus plus. So both of these conditions then essentially imply, both of these conditions imply this equation, and this is a very important equation. So far I haven't really motivated this antipodal matching condition, and it's been asked on Slack, and I tried to answer it. But what I'm going to show now is actually, I think it's the cleanest proof that the antipodal matching condition has to hold. So at this point, I'm not sure whether this equation is true or not, but I'm going to show in a moment that it follows from the subleading soft theorem. Yeah, so this is the essence of what I was trying to say on Monday. So let's see how this sort of conservation law is equivalent to the soft theorem. So to see that, let me just demand, so impose that this is a symmetry of the S matrix. So the statement that this equation is a symmetry of the S matrix is that that essentially the commutator, that this charge commutes with the S matrix. So we can write it as QS minus SQ minus. So here we have sandwiched between in and out states, as one would compute the S matrix, is equal to 0. Yeah, so let's see what this means. Let's see what this equation tells us. So now we have some information on what Q and Q minus are. So we can use the split into hard and soft charges to rewrite this equation as follows. So this is the same as saying that an insertion, that the commutator, let me just be a bit more schematic now, the commutator of the soft, so recall that Q is Q soft plus Q hard. So it trivially follows the commutator of Q soft with S has to be equal to minus the commutator of Q hard with S. Yes. And now the punchline is that I actually know how to compute. So one can compute the left-hand side. And how do we compute the left-hand side? Well, we take the expression of Q soft, which I haven't really written down, but it was an exercise to show that the Q soft whose commutator with CZZ gives you a term like this, takes the following form. So it's sort of, I think, minus a half integral over du integral over the sphere. So d squared z u dz cubed yz. Okay, so it's actually, sorry, and then there is an n z bar. So it's not hard to see that if you just take this commutator, the commutator of Q soft with CZZ, you're going to reproduce this this shift in CZZ. Okay, and now insert it into the S matrix. But the important point here is that, so this is an integral from minus infinity to infinity over du of u and zz integrated over the sphere with some weight, some kind of this sort of weight function. But the crucial thing is that we can break down this formula into two parts, and one of them we can define to be n z bar 1 as the integral over du of u n z bar. And I'm going to now argue that this is a subleading soft graviton. So how do we see this? One way to see this is to notice that this integral is nothing but the limit as omega goes to 0 of an integral from minus infinity to infinity of du u e to the I omega u and z bar. Yeah, here I'm manually just inserting this factor. I'm taking the limit as omega goes to 0, so this is trivially equivalent to this expression. But now we also notice that this is also the same as limit as omega goes to 0 of d by the omega. So this is just a function of u, z, and z bar. So I can just reproduce this u factor here by taking a derivative with respect to omega of this expression. So minus infinity to infinity, du and z bar. But this guy can be shown by similar arguments and using mode expansion near scribe plus, for example. This is just the limit as omega goes to 0 of d by the omega a minus omega x hat minus a plus dagger omega x hat. So this is Q hat, the momentum. It's the momentum of a soft of a graviton at this point, but I'm taking the limit as omega goes to 0 of this expression. So let's break it down a little bit. So this can also be written as limit as omega goes to 0 of 1 plus omega d by the omega of this particular combination. Minus a plus dagger, which are both functions of omega x hat. And this, you can show that this operator projects out the leading soft pole. So if one just had limit as omega goes to 0 of a dagger omega x inserted into the S matrix, actually let me write it this way. Let's say we have an outgoing soft photon. This is this would just be this leading soft factor plus corrections, plus order omega to the 0 corrections, divided by out S in. But we showed last time that this guy is proportional to 1 over omega, and 1 plus omega d by the omega acting on 1 over omega just gives 0. So acting with this operator on this linear antisymmetric linear combination of anti-Hermitian combination of soft photons essentially projects out this piece, and in the limit omega goes to 0 just picks out the subleading soft factor. Okay, is this clear? So the upshot is that n z bar 1 is in one-to-one correspondence to a subleading soft graviton. And I'm almost done. Because now that we established that that the insertion of Q soft into the S matrix is essentially a weighted integral over the sphere of a subleading soft photon, I can just evaluate it, right? I can just write out Q soft S in is equal to this integral over the sphere, this integral over the sphere, dz cubed yz. So this is what we had before, and we just showed that this is like a subleading okay. Limit as omega goes to 0, 1 plus omega divided omega, a omega q hat of z in z bar s in, right? But now this part is given by the subleading soft theorem. So this is the same as just integral over the sphere of dz cubed yz s1, which is a function of q and pk. Well, it's actually it involves a sum over k s in. And now the final thing is that, which I haven't gone through last time, but you can see it in the notes, is that, so in particular, it corresponds, in this case, it would be a negative helicity graviton I'm inserting. But this, we wrote down a formula for this last time. So this was something like sum over k, pk dot epsilon minus pk dot q, q dot jk dot epsilon minus, and say all k from 1 to n are scalars. Just for simplicity, it can be generalized to scattering processes where you have arbitrary spin particles scattering, like for example, just graviton scattering in pure gravity, but it turns out to be a bit simpler if you just restrict to external particles to be scalars. And this you can just compute. And the way to compute it is to use these parametrizations for these massless momenta, so pk and q, and let me just write it down. It's going to be, we're going to see them again today. So one can parametrize them as follows. So q, a null vector can be parametrized in terms of coordinates on the sphere as 1, and then z plus z bar divided by 1 plus z bar, minus I z minus z bar divided by 1 plus z bar, 1 minus z bar divided by 1 plus z bar. And similarly for pk, but just replacing these z's by zk's. And then this angular momentum operator, you can also write in terms of these coordinates, because as I said last time, this is it is the usual momentum space version of the usual Lorenz generators. So mu minus pk mu. And after some algebra, you can show that this is equal to just sum over k, and then you have some expression, which just depends on z and zk, right? So 1 plus z bar k divided by z bar k minus z bar, 1 plus k z bar k, omega k d by the omega k. So these derivatives come from the action. So this j is a differential operator, so it's natural that upon parametrizations of this form, you're going to end up with a differential operator. And then there is another contribution, which is z minus zk squared divided by z bar k minus z bar d by dzk. Okay, so this is it's just the subleading soft factor in this parametrization here. So now that we have that, we can just plug it into this formula. So you plug it here, we integrate by parts to move this derivative to act on this factor, on this term. And it turns out that acting with 3 derivatives on these guys localizes these terms onto delta functions and derivatives of delta functions. That's the key thing. And by doing that, you find that essentially out Q soft S in is equal to minus the action of the hard charge. So, but this is a consequence of the subleading soft theorem. It's not a priori obvious, but it confirms this relationship we started off with. Okay, one thing I want to say is that one recovers basically global these global conservation laws associated with Lorenz symmetry by setting yz to be 1, z and z squared. So one gets, and similarly for yz bar, so you get angular momentum conservation. Essentially because this particular mode, if you set yz to be 1, z or z bar, this guy is just going to vanish. So this particular mode of the subleading soft factor is going to be 0. But on the right-hand side, the right-hand side can also be evaluated by doing this integration by parts. And one equivalently finds something of the form 0 is equal to some relation. And there's going to be 6 relations, 1 for each choice of yz, and those are just going to reduce to the Lorenz sort of. I'm also going to write it down again today when we study celestial amplitudes, but it's going to be equivalent to Lorenz symmetry of the S matrix, so sort of global conformal symmetry on the celestial sphere. So, okay, so I think I'm sort of done with kind of trying to. I'm not sure if this is more clear now than it was on Monday. I feel like perhaps. Yeah, so if people have any questions about any of these steps, now it's a good time to ask, and I can go in more detail. And there is a similar analysis one can do for example, for the leading soft theorem. Yes, Dimitri?
So I have maybe a naive question. So this symmetries Q, they were derived as asymptotic symmetries, right?
Yes.
But then this, the fact that they commute with a Scattering matrix means that they are actually not just asymptotic symmetries, they're just the symmetries, full symmetries. Am I wrong?
But by asymptotic symmetry, I mean, the asymptotic symmetries can be thought of as really being, they're large gauge symmetries, so they're sort of like global symmetries of the S matrix in some sense. And they're not by, yeah, sometimes there is this confusing distinction between what it means for something to be an asymptotic symmetry. But here, these are really symmetries that if once you take the limit, the strict limit as R goes to infinity, these guys survive. I mean, they're not going to reduce to just Poincaré, for example. They're still going to be non-vanishing symmetries. It's strictly at scribe. Okay, I'm not sure if that answers your question, but you can really think about the S matrix as a map between data at scri minus and the data at scri plus, and these symmetries really act non-trivially on both these data in the strict, R goes to infinity limit.
I'm not sure that I'm very correct here saying that, well, if there is a commutation between an operator and S matrix, does it imply that there's that also the Hamiltonian, for example, theory commutes with this Q?
Yeah, and in fact, that would be energy conservation. I think that this commutation relation can be thought of as a conservation law. So we're really just saying that these charges, in the standard sense, Clay also described yesterday, as you think about an asymptotically flat space, right? You can consider a space like slides. These charges are going to be defined. Okay, they're going to be defined somewhere here at these boundaries of these slices. But of course, you can there's two special Cauchy slices. One of them is scribe minus and the other one is scribe plus. There are all of these intermediate space-like slices, okay? But these charges, this conservation law really tells you that the charge here is going to be the same as the charge here under evolution. And that's the statement that it commutes with the S matrix. I'm not sure if that makes sense.
I also remember Clay's lectures define the charges. I have another question, maybe a clarification. So about the statement that people didn't know how to apply new scattering matrix in asymptotic flat spaces. So what does it really mean? And what I mean, QFT in some sense is the scattering of fields in flat space, right? So what's different from QFT in QFT?
Oh, in QFT, I think it's mostly, and I think the easiest example is QED. If you look at QFT textbook, you always, all of the gauge symmetries are essentially fixed. The radiative, you're not allowed to do any gauge symmetries on, for example, like data at infinity. So here we're sort of, okay, typical QFT textbook analysis overfixes. Fixes too much of the redundancy. So in particular, it kills these interesting large gauge symmetries which act non-trivially on the data at infinity. So it's similar to gravity. Similar situation here in gravity. Of course, if you ignore completely, if you just gauge fix, you can say that all of your asymptotic symmetries are just Poincaré, and there's nothing wrong with doing so in gravity, and that's okay. And then you can define, then you can go ahead and I guess compute S matrices. But the non-trivial observation is that the existence of soft theorems actually tells you that it's not quite consistent to do these.
Maybe I can make a comment. I'm not sure if it's helpful, but so if you do this asymptotics analysis in ADS, you do get the finite group of conformal field theory. Well, except if you do ADS3 and then you get the Virasoro of the dual CFT. So in that sense, this really gives symmetries of the full theory.
Yeah, exactly. And I should also say that this is a special also to, what I'm saying here is sort of special to 4 dimensions, because it's this case when the sub-leading soft graviton theorem actually implies this enhancement to full Virasoro. If you and similar comments apply to BMS. In higher dimensions, it's more subtle, because at leading order, at least, both BMS group and extended BMS groups actually collapse to Poincaré, which is similar to, I guess, ADS CFT kind of story, that ADS3 CFT2 is special. And we're going to see actually later today that there is some connection to ADS3 CFT2 also in this case. One can choose particular slicing of Minkowski space. So also, if you think about the other way, sometimes in CFT it's useful to think about the embedding formalism. So here we're sort of going the other way, thinking about your null vectors, for example, in flat spaces.
I think Igor had a question afterwards. Yeah.
Yes, but related to the last question, I have sent to the chat a paper by Geoff Comper and his collaborators. I think they try to generalize the analysis of asymptotic symmetries in the presence of cosmological constants. So it may be helpful to answer the last question. I do not know, it's outside my understanding now. The question which I would like to ask is, could you please return to the slides where you show the commutation relation between the NZZ and CZZ?
Sure, I have, well, I claimed that these are the commutation relations. I haven't proved them here or previously, but the point is that there's various ways in which one can show them, and one of them is to start from the classical analysis of the symplectic, as you said yesterday, Ayerwald, so on and so forth, or Ashtekar also just do a canonical analysis and arrive at these commutation relations, which in that case would just involve Poisson brackets and then just promote them to commutators. And then this is how one way to arrive at these relations. But I'm not sure what the question was. Sorry, I feel like I.
Okay, then I will accept these commutation relations for now. I am even building a personal dictionary between Ashiteka, Valdi, Barnik, etc. But anyway, I know from non-relativistic quantum mechanics that I have a commutation relation for X and P, okay? And this implies the uncertainty principle that we all are familiar with. So this commutation relation, can I understand this as an uncertainty relation between the NZZ and CZWW?
Let's see. Yeah, okay. Typically, I need to think about this, but I think in this analysis, we're actually setting A by G equal to 1, and I cannot. No. Oh, sorry. No, I think there has to be a factor of G here, which as you take to 0. Is this what you're talking about? If there is some small parameter, which is the Newton's constant. But what I just said, I need to.
No, the point is, okay, there might be an I factor and a G Newton, or depending of the theory KD, you have the alpha prime, the alpha or the electric charge. But the point is, you have a commutation relations, and this implies an uncertainty relations. So the question is about the physical measurability of the charge associated to the asymptotic symmetries at the quantum level now. The
measurability of all of these is given by the memory effect, which in gravity, okay, it's still a classical effect. So at least that the super translations that relate. So there is this, and I'm sure you're familiar with this, that, for example, if you have some scattering process in which you have non-trivial, second third derivative of the quadrupole moment. An example of this would be, for example, if you have two particles coming in at some constant velocities and then suddenly annihilating or something, two black holes, then there's going to be an initial second derivative of the quadrupole moment, which is going to be non-zero. At the end of the day, we're going to have zero quadrupole moment, and there is a net change in the second derivative of the quadrupole moment, which is essentially related, which essentially gives rise to this memory effect, which would be a relative displacement in the trajectories of two asymptotic inertial or BMS detectors. And I know you put this in the chat, and you said, as far as I can tell, everything you said there is correct. So in other words, there is a measurable effect associated with all that I'm saying, and the way one can do such a measurement is essentially by looking at the net relative displacement. Like, for example, at LIGO, when you measure the oscillations in space-time, there's going to also be a net permanent sort of displacement between the arms or mirrors or whatever in the detector. And I think there's proposals, for example, in the gravity case, to measure this in future gravitational wave experiments. But it's a classical, again, I mean, as far as I can tell, it's a classical effect, and it follows from Einstein's equations. For a long time, it's believed that perhaps the memory effect in QED has some sort of quantum nature to it, but okay, I'm still a bit, I'm actually a bit confused about that one. So
okay, I took the liberty of sending to the chat a paper by Bosso and Poratti. I think they articulate my question in a more formal way. So maybe I can create a thread in the Slack to discuss this in more details.
Yeah, I'm aware. I know these papers, and I haven't studied them enough, although I meant to be able to exactly point out
yes,
what
they are
what we're doing wrong, or what I couldn't comment right now on them. But if you want, I can have a more careful look at them and try to kind of.
Yes, my only concern with their paper is that they are arguing about the possibility that the soft charts are not measurable because of the uncertainty relations following from these commutators. But I completely agree with you. It's a classical analysis at now.
The argument there is, now I remember actually, I think was that, okay, you have to wait. If you were actually to measure the memory effect at Scry, you would have to wait for an infinite amount of time to be able to measure, like naively, right? There is the uncertainty principle saying that if you want to measure a zero frequency thing, right, then
yes, exactly. That's the point.
Frequency is sort of dual to time, and so you'd have to wait an infinite amount of time, or retarded time if you want, to be able to measure strictly zero, this zero mode, right?
Yes, you nailed exactly the point I was thinking. It's exactly this. If you want to measure these soft charts, you would need an infinite time to do so. That's their argument.
Right.
But as you, I have not read their papers in detail, so I cannot comment more than that.
Yeah, but the thing is that, okay, the memory effect is also measurable if you're at some large finite radius inside the ball. You don't have to be at Scry to be able to measure it. That's one thing. And secondly, Yeah, okay. There is some subtleties about having strictly zero energy gravitons, for example, you want to measure, or just low energy gravitons. And of course, soft theorems in particle physics are important because, you know, they're a statement about not just necessarily strictly zero energy stuff, right? But
Right.
yeah. Anyways,
Okay.
there is another question perhaps before.
Perhaps, because we need to have some time for lunch. So
Yeah.
go ahead.
Okay, no, thank you very much. I will not extend.
I'm happy to discuss further, but sorry, I don't remember those papers very well actually, so I'm not sure if I can say useful things.
Okay, I apologize for extending too much this point.
No, this was.
Thank you very much.
You have your hand raised, Jivan. Do you want to ask a question?
Hi, yeah, I have a question. So you derive the algebra of this large diffeomorphisms by requiring that these vector fields preserve the fall-off conditions of the metric, right?
Correct, yes.
So could you remind where those fall-off conditions came from, or were they a choice that asymptotically flat spacetimes have? Or
Yeah, so the boundary, of course, is, for example, Andy likes to say that it's like an art, not a science, to pick the boundary conditions that don't, you know, you don't want to fix too much or too little. And it just so happens, I mean, those boundary conditions are basically, so if you remember, oops, sorry, just very briefly, yesterday I wrote down an expression for this asymptotically, when Bondi and Metzner and Sachs and van der Burg were studying these spacetimes, right, they're looking at some kind of, they're imagining a setup where you had some kind of source of gravitational radiation somewhere in the middle of spacetime. So for example, two colliding black holes or something with some non-trivial quadrupole moment, right? And then they wanted to know what the sort of radiation describes such physical processes or geometries, take the following form. So 2 du dr plus 2r squared gamma zz bar dz bar. So this is just the Minkowski metric. And then we have perturbations. So perturbations, linear perturbations on top of this Minkowski background. So this is supposed to be what happens, you know, what would happen somewhere really far away from such sources. And so there is, one can have this Bondi mass term, so du squared, then plus r czz plus r, oh, sorry, r czz dz squared plus r cz bar z bar dz bar squared plus other stuff, so which are subleading in 1 over r. And the reason, so if you look at their original papers, 62, between, I don't know, around this, in the 60s, this came about, of course, here you had to fix a gauge, right? This is not the most general thing one can write down, right? Generically, you could write down, for example, you know, GRR terms and other GRU terms at all orders, right? At 1 over r, for example, and so on and so forth. But they, first of all, they fixed the gauge. So fixed a gauge, which is called the Bondi gauge, where essentially just fixed, I sort of said this yesterday, they fixed GRR to be equal to 0, which essentially meant that radiation, they're looking at radiation that propagates outwards along the radial direction. So that means there's no longitudinal, sorry, not just GRR, GR mu more generally. So GR mu is equal to 0 in Bondi gauge. So this means there's no longitudinal component of the metric along the radial direction. It's the statement that radiation propagates outwards. And the other condition was that there's no ZZ bar, the transverse part of the metric, this GH AB sort of on this. They fixed, right? It's a condition that the metric is transverse traceless on the sphere, or in other words, they're keeping, right, fixed area surfaces. Yeah, that's the fixed radius surfaces or spheres. They impose the condition that those areas are fixed and equal to 4 pi r squared. At every fixed r, you don't have weird deformations of these surfaces, and that essentially gives you the condition that there is no GZZ bar corrections. So you only have CZZ and CZ bar, Z bar, for example, corrections to the metric. And then this was also, I mean, shown to be consistent with asymptotically flat conditions. And then once you believe that there's no, I mean, these are the fall-offs with R, of course, but again, these are not, it's physically motivated. This gauge fixing in part is physically motivated, and then, you know, killing other components, imposing that, for example, GUR appears at 1 over R squared, I guess comes, I have to remind myself, yeah, I think comes from Einstein's equations, right? Then you want, for example, you want your perturbations to be consistent with Einstein's equations, and then you find, as I said yesterday, constraints on what they can be. But to this order in R, so for example, to order 1 in a large R expansion, you see that the asymptotic symmetry group would essentially preserve the Minkowski metric up to corrections which appear at these specified orders here, okay? And so this is how you, and Igor had a question yesterday, where a big O or small o, definitely big O, because you don't want them to vanish. So the condition would be something like G, the derivative of GUU with respect to some vector field psi is equal to something which is order 1 over R, right? And similarly, you can read off all of the other constraints from sort of this metric. And these are then a bunch of differential equations. You can solve them order by order in R. So they start, the first non-trivial order is order R squared. And if you look at all of them, that's already going to tell you something about these perturbations and so on and so forth. Then you look at order R, and then you find some equations and so on and so forth. Does that make sense?
Yeah, I see. So these are like these are more like physically motivated fall-off conditions, right?
Yeah. Yes. Yeah. I mean.
So I was just wondering, like, if I had chosen different fall-off conditions, like, how would it affect my algebra? Like, how sensitive is the algebra to the choice of fall-off?
Yeah, it's very sensitive. You can completely kill this BMS group if you impose, for example, 2 strong fall-offs. So you can demand that there's just no other corrections, and then of course your symmetry group. Yeah. The simplest example is just say, you know, there's nothing else, and then of course the symmetry group of just Minkowski space is not going to include BMS, right? It's the fact that you're allowing for these guys, and in particular, if you said that, okay, there is no RCZZ term, and your first shear kind of component comes at order 1, that would also kill your super translations, for example. It's important that you're allowing.
So I guess then these are the unique fall-off conditions which give you the BMS algebra.
Like unique fall-off conditions. I should say that in Bondi gauge, these are the fall-off conditions. One can do similar analysis in harmonic gauge, and the fall-offs in harmonic gauge look a bit different, if I remember correctly. But of course,
I don't mean in different gauges. Like say, let us fix a gauge, and in that particular gauge, I scan over different fall-off conditions, and I just want to know, like, which of the fall-off conditions would give me the BMS algebra.
I should say that they're certainly not unique, because you can allow even weaker fall-offs, in which case you're going to enhance your BMS even further. And in fact, this has been argued in some papers to be related to things like sub-leading soft theorems and so on and so forth. So these are certainly not the unique these are not the unique, as far as I can tell, boundary conditions that will have, at least as a subgroup, the BMS, right? And in part, yeah, I wouldn't say that they're the unique ones, right? You can allow for other less strong conditions, which will enhance your symmetry group even further. But deciding, yeah, I mean, what the symmetry group, I think this is one of the, as I'm going to get to hopefully tomorrow, one of the very interesting questions in this program is what are the symmetries? Like we don't really know what the full story is, I think. And it's a great question. But...
I see. Thank you very much.
Okay. So Igor, if you don't mind, can we postpone your question to the next discussion session or maybe after the lecture of Anna-Marie? Because I think we need some time for lunch. And so Anna also needs to take some rest and she will have to teach in less than an hour.
No worries, I'm happy to hang out here with Igor if he has more questions, but perhaps discuss. I don't know if we want this to be recorded. I'm happy to chat till 7.
Yeah, we need probably technical reasons we need to stop this session, and but the room will be open for discussions, of course.
Okay.
Okay, so I propose we officially end this discussion with a round of applause for Anna for such a nice detailed discussion. And,
thank you very much.